All right. So, few announcements. Midterm. Yeah. Everybody do the midterm dance? It's a dance that comes from here. So yeah, I posted some fun things for you to read on Piazza, including two final exams from earlier years. So you can get a glimpse into my psyche of how I ask questions related to what you do. Now when you look at these 19 to 23-page documents, you'll probably be like, but those are for 3-hour finals, so they're longer than what you'll experience. And they also cover an entire course, half of which you haven't taken yet. So if there are questions there, you're like, oh, we didn't learn this. Yeah, that's right. You didn't learn that. Right? So the things that you're kind of thinking like, oh, this sounds like something that was on one of those labs. I have no idea what's going on. Get an idea about what's going on. Yes, do the exercise again, or read up, or try to think of something autonomous. It is pretty heavy on the did you do the first assignment or not type of question. It is closed book, so no photos, no notes, no nothing. You're stripped bare and as you enter the classroom. You can bring a pencil, chocolate, and the calculator. Chocolate is important. I won't be there, but I'll be there in spirit. I'm trying to see who's going to proctor for me, but it should be somebody who can either answer your questions or operate a mobile device and call me up if there are any questions. So you should be fine. So we'll be in class next Wednesday. Any questions about midterm? Who's excited? Woo! Yeah. Yeah. It's to be in every class. Yes. I'll leave it at that. Any questions with midterm? Oh, outside? Oh, what topics are for the midterm? Oh, that's a good question. Thank you. Yes. Everything until Wednesday. So everything that we've covered in lecture, every homework that we've done so far, everything that you've seen in your lives, all of that could be on the midterm. So if you are looking through the slides and so forth, pick up the little anecdotes that I mentioned so forth. Like I may ask questions about them. You'll see in this practice exams like what types of questions I may ask you two-fold questions about like, hey, is this statement true or false? Did I say that? Is that something that's like sounds plausible? Or I'll ask you to be like, hey, look, here's a computer and here's some information about the computer. Hack it. You know, so like write a little essay about how you're going to hack it. Okay. So those are the range of questions I'm going to guess. Exam is also more than 100%, so you don't have to solve every single part of it. I've graded on my famous 110% scale. So there's some leeway for error. I don't curve. I think curving is the right thing to do. If there's instances where an entire class can have high grades, there's instances where an entire class cannot have high grades. It's a little bit, the correction that you get from curving doesn't compensate for the lack of opportunity, having a limited number of days or something like that. So I don't grade on curve, but I try to pre-curve it a little bit by having 100%. So that if there are questions that are hard, they can be skipped without any penalty. Other questions? Those are good questions, thank you. Anyone else? Yeah. In spirit, we'll go through it. We've been going through it all semester. But if you show up for office hours or something with questions from the midterm, I'm happy to go through that. Or if you have questions on Piazza, you can ask about this question this year here. I have no idea what's going on. Can you tell us what's going on? I'm happy to do that. But in general, I think it's more like you guys can go around in Piazza and be like, hey, I'm thinking about this question, and like, what do you guys think about this and that? What's the lecture that's corresponding? Feel free to crowdsource it a little bit. I'm happy to be involved in that, but I wasn't planning on using actual lecture time going through all data. The purpose of this class is not to gear you up for exams, it's just educating with new material. Right? Sounds good? Yes?
Also, today not included.
Not included? Everything's included until the exam. Yeah. Oh. Until the minute the exam starts, everything that you learn about computer security is on the exam. Yes. Yeah. Yeah. It's included. More questions? How is JoyLab? Like I asked you before, but any outstanding questions? People are doing okay? Surviving? Everybody has started, right? Some people are not nodding. Okay, good. Good, okay. And it's been kind of fun, right? Thanks, yes. Maybe? Yeah. Okay. Cool. So, we're now kind of venturing over kind of the breadth of security. So we're taking a bunch of kind of different topics that constitute some of the many domains that security entails. And today, we're going to talk about network security. So some of these obscure concepts that I mentioned in the past may make a little bit more sense after today. How many people have taken some sort of networks course? Aha, all right. I feared this would be the case, which is why I'm starting with a networking primer. Okay, the internet is a series of tubes. Have we heard this statement? Am I so old? Okay. What is the internet? So let's do kind of like a quick primer about what it is. So if I ask you what the internet is, does anybody have a good answer for it?
A bunch of computers connected.
Pretty much, yeah. It's a bunch of computers of various forms. Some of these computers are called routers, some of these computers are called something else, that are connected by some sort of wiring, right? With some of them are wireless, but most of them are kind of wired in the background. They're divided up into this kind of hierarchical structure, just like you can picture that you have like a driveway in your house and so forth. You have a street that you live at, and then there's like highways and so forth. And that whole analogy also holds true for the internet. So you have these backbones here. So suppose you're this user here at this really ancient looking computer right there. Now, you're in your house and you're on your wireless. That means that you have a wireless connection to your home router, like your wireless router. That one has a physical connection to the ISP through a number of hops that we can skip. The ISP itself has an internal network, and eventually they have a fiber connection going probably somewhere else, to AT&T or maybe to Comcast, or one of these big players. And then so on and so forth. So these big backbone ISPs have these massive links between them. That means that when you're sending a packet, you're actually traversing a number of different hops. A hop here is a computer that's just saying, hey, I got a packet, I'm supposed to send it onward somewhere. We'll talk about what constitutes a packet in just a little bit. Just going to show you like how this really looks. Let me just open up a session here and just kind of show you a trace route, for instance. Suppose I go to, let me just log in, yeah, somewhere here in the US, that's fine. See if this works. Okay, while we wait for this. Oh, there we go. Probably what happened was that it was spawning up a new container for me to log on. Ta-da-da-da. Ta-da. Okay, I'm going to talk to some other node on the internet. I'm going to send a little packet, one packet called ping. And ping contains the character set A, B, C, D, and so forth. It contains no information of value. All it does is really is that it has a destination and a source of where I'm sending it from. So I can now ping, and let me just ping something that has a name, like google.com. Oh, I can't. Great. Let's pick another computer then. That is disappointing. Let's try another machine here, since I have a few. Duplicate. I'll spend most of the class waiting to log in. The internet is slow also. Did you guys know that? Yeah. Okay, so here we are. Here's some machine somewhere. I'm going to ping google.com. Now, what does it mean? It means that there's actually now, and we'll learn this later in class, there's some process that takes place that's able to say that, oh, google.com, you mean 216.58.209.111? Or 110, I guess. So that's an IP address that corresponds to google.com. Now, it's actually not the only IP address that corresponds to google.com. If I ping it again, I may get that. But if I ping, I don't know, .google.com, I get a totally different address. Here's .100. And this is actually an address that's specifically chosen for me here because it's a part of Google that's close to where this machine is physically residing. It has low round-trip time. Okay? Anyway, what am I doing? I'm sending a packet to this particular machine. and it's responding to me. It sent me back 64 bytes from this node over here. Notice that then you get a weird name here back. Well, actually, this is just a part of Google's massive infrastructure. The 1E100, anybody know what number that is? It's a Google, which is what the company's named after. So, giant number into the 100. Anyway, so this is their content distribution network, just for fun. Anyway, so we've just sent a packet here. What I wanted to show you was something a little bit cooler. Traceroute, google.com. Oh, really? What's up with that? Okay, well, let's wait for that. What I'm going to do, I'm going to now send, instead of sending just a packet to Google, and having the packet be kind of transparently routed by all the places in between, I'm going to send a packet that has a short time to live, meaning that like, oh, if I've traversed more than one hop, I'm just going to give up and die. That means that some router in there just like notices this wimpy packet coming in and then, and it's just like, there's a packet that died. It sends me a message that says, hey, I just lost the packet because of some reasons. It ran out. As a part of sending me that information, I get to know what the router is. So I'm actually going to be able to increase that time to live gradually and get to know all the routers that are going to be touching that packet. So we get to see the route between this machine and Google. This would be really fun. There we go. Trace route. Trace path. Fine. Okay. Google.com. Oh, what are we doing? We're sending a bunch of packets. So the first one that we contacted was some router this is at Reykjavik University. So it's a local router there, and then it gets two responses from a good enough person. This is the RHNet, which is the university network in Aston, goes to several hops over there that are pretty similar here. It eventually goes to NordUninet, so it went over to Sweden for whatever reason. And then ends up here, and so it's Norden, and then there's Iceland, then Denmark, and then Sweden. And then there's no replies because they're kind of masking what's happening inside the internal network of Google. And then I guess eventually it's going to be like a response.
No, they have to really go through that network.
Yeah, so the number here at the front is the TTL, the time to live, saying like, if I want to go through 24, can I get a response? So it's this dark matter on the internet. Let's pick some network that's less draconian. Any takers? What's a good URL? Anybody have a website?
Rolls.org.
Rolls.
ROLZ.org.
Rolls.com.
Org.
Org. Okay, let's see what happens now. Let's look at it the same place. Weird. Let's pick something in Europe.
Here, I don't know.
Let's do like BMW.Germany. Okay, yeah, okay. Okay. So now we're somewhere in Denmark, and we'll go over here, and we're in Stockholm over here, and then Hamburg here. This is about Germany, and then eventually we're in Bayerske Motorwerke, BMW. That training of gigabit Ethernet. It's so verbose, it's like all for legal purposes. And then you eventually hit that kind of dark hole. But notice what's happening here on the right-hand side. You're seeing the kind of milliseconds add up over here, right? This is like how long it took to get a response from that intermediate on the internet. Fun, right? Now, this keeps adding up, right? So it took like 100-something milliseconds to just get to that destination. Is there a way for us to make that faster? If you were to kind of, with your knowledge on the internet, if you were to re-engineer the internet a little bit, could you make it faster? What does fast mean? There's really two things at work. It's about the latency. It's like how long, if I send a packet, how long until it gets received on the other end. And then there's about the volume of things I can send back and forth, right? If I can download 1 megabyte file really quickly, 1 gigabyte file really quickly or not, right? There's two different things, and those are very different things. So bandwidth, which is about the volume of traffic going back and forth, that's something that we're actively trying to improve on the internet by building more cables, thicker cables, better connections, shorter routes, all that stuff, right? So, yeah, you can now get Google Fiber and you have like, I don't know how many gigabytes per second at home, you can download things that you'll never need. Great. What about latency? How do we make latency better? If I'm talking to a server in Australia, There's some limitation about how quickly I can get packets to them. The limitation comes from this stupid guy, Einstein, right? It's like the speed of light. He like capped all communication at the speed of light. So now we can't go faster than the speed of light. We can't even redefine the speed of light to be faster. Like we're just bound by this stupid law, right? So that means that there's like an upper bound on how quickly you can get information from one side of the planet to the other side of the planet. Suppose you're a company and you have like, oh, we're making a game and it has to be really responsive, as people get pissed off and they stop using the game, right? So how do you make a game or something more responsive if you're bound by this kind of players just around the globe are not going to use your service because of latency? What would you do? Wormhole?
Get more servers.
Yeah, get servers closer to the user, right? Which is why when we pinged Google, it was actually in Sweden. Right? There's a server for Google in Sweden. Now internally there's a big network of things, but Google by itself keeps a copy of everything that you might need in several places that are geographically close to their end users. That's how we deal with latency. So that's why when you're watching the Olympics or something, you're trying to download it from something that's very close to your ISP. And there's a huge push now to having kind of better content distribution like that. It's a very interesting endeavor. Anyway, I think we got derailed a little bit. We were talking about a series of tubes. And by the way, jotting questions, because like this is not an information session, but networking. Cool, okay? The dark clouds here, they're called autonomous systems. So they're, these entities are usually owned by a single company. There can be many, many different routers and they're bridging together, but it's all part of like the AT&T network, or it's part of the Google network, or Comcast, or whatever, right? And the way they talk to each other, to know that like, hey, there's a route over there and there's another route over there, and to know that, hey, I got a packet in here and I'm going to try to send it onwards, where do I send it? Now that's an interesting question by itself. Suppose the internet was just this giant kind of tree, right? Then it would be easy to just like, oh, I'm just going to send the packet forward on the tree and it will eventually reach the only path it can reach its destination. And it's not a tree, it's a network. So just like when you are thinking about, oh, I'm going to this unknown place somewhere in Georgia, or like you're driving to California, you have a number of different routes you could take. So how do we do kind of Google Maps for the internet? How do packets figure things out? It would be kind of wasteful if every single packet that needs to be sent to the internet, of which there are many, needed to be like, oh, what's my optimal route right now? Oh, okay, oh, sorry, right? That wouldn't be very helpful. So what would be a good process by which we can get packets to their destinations efficiently? So it's already, the packet kind of entails that it's been split up, and so a packet is usually about 1,500 bytes. Now that's a good thought though. For a while they were like, oh yeah, you want to send some data? Just send all the data at once. And then like everybody else is waiting for the connection that's dealing one bit at a time, just as you wait for your giant, whatever it is that you're sending to be done. It doesn't quite work, it's not so good. So we break big things into smaller packets, so they're at most 1,500 bytes, and then we send those. But suppose you have a packet. The packet has like been sent from one of the computers over there, and someone used to find his way over there. And you don't want the packet to be fully aware of every single possible computer in the middle, because that's a lot of information, and it's changing all the time. Like, somebody went bombed AT&T, for whatever reason, right? And these things could be severed, and you need to pick a different route. How do you deal with that? When they designed the internet, this is one of the prime considerations. Like, oh, what if somebody bombs Chicago? We need to make sure packets can get around Chicago. So they have a lot of redundancy built in. How do we have packets have information about where to go? They know where they want to go ultimately, but how do they make progress? What would be a good mechanism for this if we were to architect this? Very convenient that somebody did it for you already, huh? And what's the ticket you use? You can have more memory where? Who's remembering what? Yeah.
You could have like each of the nodes sort of like give it a pointer to where they think the next optimal node is.
There you go. That's exactly what they do. So every single node here, every single pointer is like, oh, okay, I'm situated here, and I have some limited information about how the internet works, but I get some information about who I'm peering with, and whenever I get a packet that's meant for any of these IP addresses, I'm going to send it on this link. And for the other IP addresses, I'm going to send over that link. That's it. So every single router is just kind of pushing packets slightly forward to their destination without really knowing where it's going. And there's this protocol called BGP, Border Gateway Protocol. This is an ancient protocol, really easy to attack. Attackers regularly attack this to disrupt the internet. But tries to have all these different routers, these blue nodes over here, kind of talk together and decide on the shortest routes. So they're just a random variant of Dijkstra's algorithm, saying like, hey, what are the shortest routes now between us right now? Oh, cool, okay, so we should maybe route some of these apertures over there and these ones down. Ultimately, each router just stores a list of things where it can make progress towards the destination for the largest number of packets. Make sense? Great. Now, the messages themselves, the packets, they're using something called TCP/IP, which I'm sure you've seen. How many people know what TCP/IP is? Raise on yours. Ray knows. Great, you guys are dismissed. So TCP/IP is a suite of protocols, which is just really how you're going to do messaging. So let's spend some time on thinking about what that looks like. When they designed the internet, of course, what they wanted to do was be able to have something that could serve the maximum number of applications, right? But it would be really, really wasteful if you were trying to architect and be like, yeah, I'm sending in bits right now, and they're all just like, they're voice bits for like some audio call that somebody's calling, and then there's also just there's like pictures and images, and then there's intel. We're just shoving it all together, right? And somehow it's supposed to get figured out. Because there's so many different things that can go wrong. Like for instance, suppose part of your voice bits get lost, and somebody has to figure out how to do fault tolerance in that, or reconstruct the missing bits, and it all gets like really hairy if you approach the problem like this. So when the architects got together, they're like, well, let's break it up into kind of layers of complexity. And so they defined these 7 layers of what the internet is, where they're like, let's have the physical system itself, like the actual wireless node, the actual wired just hardware that connects to endpoints. Let's have that just worry about how to get bits over an Ethernet cable, or a coax cable, or over a wireless network, which we talked about on Monday. And not worry about anything that's above it. It doesn't care you're playing StarCraft. It has absolutely no interest in it. It's just trying to shuttle bits back and forth at this particular layer. This is the physical layer. Then there's one called the media layer, where you have a little bit more information about there may be other nodes that are kind of competing with it. For instance, if you're on wireless, there are various kind of wireless nodes that are also screaming at you. You have to be aware of them. Or if you're on Ethernet, there may be, you actually have to kind of wait and be. So here's actually how Ethernet works. It's kind of funny. You have all these kind of physical cables that are plugged in. And then one node is going to be like, can I? And then another node starts talking at the same time. They're like, whoa, whoa. Okay, I'll just wait a little bit. And then they'll start talking together again, and they're like, whoa! And they like back off all this time. And it's like this like awkward conversation with people looking at their feet, and then, can I? No, okay. And they're just trying to like find a spot where they can kind of talk only by themselves. And when they do this, like, oh, I heard that. Okay, cool. I'll process that information. Just broadcast this information. It's really an awkward protocol. So that's like media and media access. And then there's this central thing called the IP layer. And I'm drawing this kind of awkward hourglass over here to highlight something that's really cool, which is this this design that was deliberate during the internet to have a very narrow waist, meaning that there is simply one protocol that can bridge all the application level stuff that's further upstairs with all the more hardware-oriented stuff that's downstairs. Why do you think it would be important to have only one protocol over here? Does anybody think of a reason? Notice how you have a bunch here, and then so, same thing up there, but just one thing like mixed up. Suppose you're making any changes to the internet, right? Suppose you know, like, oh yeah, we have like a different thing, not TCP, but something else. oh, now I have to change all my drivers that run TCP on IP, I have to change all my drivers that run TCP on IP2 or whatever it is, and so forth. You have this kind of plethora of connections, of ways these things can interact that you would have to worry about, that you don't when you have this narrow. This is a brilliant design. They had a competing design somewhere in France that didn't have this, and that just died kind of Darwinian death because of the nice kind of the nice design that you get out of this in here. So this is the IP layer. All that the IP layer does here is to say, take a packet that somehow arrives from any of the applications above and just slam a source and a destination on front of it. It's like taking it and like shoving whatever it is into an envelope, putting a source and a destination on it, and just sending it down to the Ethernet layer, like, please forward this packet for me. It doesn't care if the packet gets lost. It has absolutely no value for these packets. It's oblivious to it. It has absolutely no concern over where things go. All it cares about is, let me take your stuff and shove names on it. That's it, okay? And the things that it puts on this envelope, the source and destination, are called IP addresses. Right? So, further up, TCP, which you've heard about, UTP, which you may have heard about if you played games, right? So TCP is what's called what? Transmission Control Protocol, which is responsible for sending packets reliably, meaning that like if you send a packet and then it gets stuck in a sewer somewhere because somebody was on an excavator and just buried through a cable that was currently carrying your packet and it's got lost. Or somebody had an over-provisioned router somewhere that's running so hot that it just like melts away packets sometimes. So there are all sorts of weird reasons for why things could get lost in the internet. There's like a pair of hunters somewhere that like shot a cable that like carried most of Google's workloads and stuff. And they like went up there and said, what? You shot our internet. It's like, so yeah, anyway, there's almost that. So TCP actually has a huge number of roles that it does. So it waits until it has all the right packets and it's all in the right order even. Because, yeah, when you're sending even the same file across the internet, it can be divided up into packets, and all of those could take very different journeys through the internet. And TCP on the other end is supposed to glue them together and make sure that they're all in the right order so that like your lol, whatever conversation you're having on the internet is actually fragmented correctly, right? And if it's missing a fragment, like, oh, I'm missing a packet, like, it looks like there's supposed to be a smiley here, but I don't have it. It's going to wait until that smiley arrives through Kazakhstan or wherever it got routed, and finally arrives, and then that gets transmitted upwards to the application itself, right? TCP has a lot of burden with that. The second thing that TCP does is congestion avoidance. So it is trying to slam as many packets as it can through the internet until it notices that it's kind of exceeding the healthy dose. It's starting to not get packets back fast enough, in which case it kind of halves the bandwidth that it has, and then keeps going linearly up, and then we notice it hits the bar again, it halves again. So it creates this weird sawtooth, just to kind of be gentle with other people using the internet so that it's not consuming all the bandwidth. Right? So UDP is the kind of unspoken twin of TCP. All it does is to try to send packets and then doesn't do any recovery, doesn't do any fault tolerance, doesn't do any congestion avoidance. It's in the packet with the problem. Right? Now, that's very useful for games where you're sending out so many packets about how you're killing all these people in whatever game you're playing that like you're overloading whatever network you're on. And even if some of these things get lost, who cares? Right? You don't want to spend the burden of doing congestion avoidance. You want to re-engineer exactly, did this shot happen exactly in this way? Or is this person right exactly here or there? You don't care. You just like, if you miss packet, so be it. Right? So games tend to favor UTP. One thing that TCP has going for itself, which we'll be talking about, is a little bit of security. And that it's hard for you to actually imitate somebody else's TCP session. Ha! No problem to imitate UDP. And boy, will we make use of that. And then we have other end-to-end application protocols here called NSMTP, HTTP, and so forth. One of these we've talked about extensively. HTTP, right? GET and POST and all that stuff the websites talk. They're just working over a raw TCP socket. SMTP is the way you send email. Of course, that protocol by itself is a lot of brokenness. I can send email from whoever I want, right? RTP, real-time protocol for media, a variety of others. And then, of course, on top of that, you have your email client or your browser or something, and they open up an HTTP connection using a TCP, and let's then fragment down the IP packets and so on and so forth, right? Cool stuff. Those are the 7 layers of the internet, right? And this is what we're going to care about in the course, these layers. I'm not going to have time to talk about all of them. We're going to talk about TCP, UDP, IP, Ethernet. And then we'll actually talk a little bit about wireless, but that's in the next class. By the way, any questions? Shout them out. Okay? Now, let's start with these end-to-end. Yeah, go ahead.
Where did the packets get lost in this?
Where do they end up?
Yeah.
This giant black hole, somewhere that collects all your lost packets. It's actually a variety of things. Usually what happens is that somebody's sending packets faster than the receiving end can receive it, and it has like a buffer, and it's a limited buffer because it's like a fixed hardware thing, so it's like 250 megabytes of things that you can keep. And then once you exceed the 250 megabytes, it's like, well, I could kick something out, or I could just drop the new thing. So it tends to just drop the new thing and not record it in this limited memory, in which case whoever sent it has to still have to keep a copy of it, or it already dropped it by itself, in which case the actual sender will have to figure out that, like, I sent this and it didn't arrive, right? So make a claim with Amazon or whatever. You can just resend the same information there, right? And yeah, there's mysterious reasons for some packet loss. It's amazing. More questions? Okay. The end-to-end principle. This is a really, really cool idea here. So imagine you were trying to tackle this whole packet loss issue that you mentioned. So suppose you were trying to like engineer and be like, well, we kind of want to make sure that not just that packets don't get lost, but that they don't get garbled. What if like there was space rays that attacked your cable and injected bits into various places, which happens, and flip things around. So instead of saying lol, you said WTF, right? And your conversation has now gone completely downward, right? Just cosmically, there was something that made this happen and shifted the right bits, right? You don't want that to happen, so you'd like to detect those types of things. The question is, where do you try to detect it? At what layer? And this is something that eluded engineers for a little while. That in fact, suppose you have every single layer trying to do detection of whether or not something is corrupt, with just like a checksum. It is still the case that the endpoints themselves, whatever application that are using it, are going to have to do those types of checksums by themselves anyway. Right? So if you think about it, applications think that they're talking to other applications, right? I'm just a Snapchat thing, I'm opening a new Snapchat instance, or whatever. I'm a web browser and I connect to websites, right? So that's the level at which they're operating. Underneath that, there's TCP. It's like, I am going to be connecting to somebody else who speaks TCP. I'm sending packets in a particular order, and I'm doing all this stuff, right? And I talk to an IP protocol. I talk to the network, and that's why I send an IP packet, it's broken down. And then it gets sent to some intermediary that understands IP and routes it forward. And underneath that, there's actually like, here, I'm a network card, and I'm talking to my router who also has a network card, and I'm sending bits here of this wire, and so forth, right? And the end-to-end protocol is effectively saying that no matter how you're getting information from anything in the application, the intermediary here, it doesn't care that you're playing StarCraft. It doesn't care that it's an email. It doesn't have to care. It is not supposed to be doing any checks of whether or not the email is malformatted, if you're missing some StarCraft packets, if some location information was lost. It shouldn't really care about anything all that, just like, let's get the envelope closer to its destination. Just like FedEx, right? FedEx isn't supposed to be like, oh, like checking every, smells kind of funny, I'm gonna throw it out, right? Like that's too much to ask for FedEx. And it doesn't help anyway, because by the end, when you open the envelope, you're gonna check whether or not it smells foul, right? Right? I don't know if you check your FedEx envelopes. So the design was deliberately made to have this be as fast as possible, its intermediate things, and to do as minimal checks as it needs to, so that everybody's imagining that they're just talking end to end with one another. So no need to understand application launching in a network except with end hosts, much cleaner design. Can you imagine how complex routers have to be if they have to have full awareness of all the applications that they could be served. Just updating the router would have, you have to do that every 2 days, right? It's like, oh, there's a new step protocol. All right, so how do we implement this different layers? So let's look at what a packet really looks like, okay? Suppose you have your application message. This is your ha-ha-ha lol message that you're sending to your sister. It's your data. And nobody cares what your data really is. What happens is that it's sent down to the next layer, which is the TCP layer, where it's fragmented into multiple different packets, 1,500 bytes or less. And at the very front of every single packet, you put a TCP header. This is your envelope, if you like. And that happens for every single packet, and it's ordered to how it's broken down. And then TCP is going to talk to its IP layer and say, hey, can you send this on the internet? And the IP layer is going to look at this entire blob over here and say, hey, I don't care what's in there, I don't even care about the TCP header. I'm just going to take this data, that is now a message of the size I support, and I'm going to put my IP header on top of it. The IP header contains source and destination, and a few other things. And then that gets sent on to link layer. The link layer will also set its own header on it, which is the Ethernet header, and also a trailer. What is the trailer here? It's just saying like, hey, I'm talking, okay, here's my packet, okay, I'm done talking, right? That's what the Ethernet is really shouting at, right? Okay? And so when it gets received on the other end, suppose like here's some host, and the host is talking, here's the client talking to the protocol itself. You get this additional frame that's added to here. It's talking to the physical wireless adapter, in this case here, a wired adapter. You get sent to the router, and the router is like, hey, okay, I see here there's like a destination that's being put here by this Ethernet layer. It's supposed to go to this other router, it's supposed to go to this other computer that's connected to this router. So what it does is that it just takes this header here and changes it to like, oh, okay, here, it's supposed to go over here. Right? This is routing. It's to forward the message onwards, one hop at a time. Okay? And then eventually it makes it here into the LAN router. And then these layers gradually will shut off. They will open the envelopes and look at what's inside and kind of shut off these headers and trailers that are added on. And eventually the server on the other end ends up with just the data, oblivious to all the misfortune that has been done. Pretty clean, right? It's a good design. The router itself, yeah, it never even looked at the data. It didn't care. Just, oh, where's the next thing to send? It's like a robot. Now, what we just talked about here was that the router someone was able to figure out that it was supposed to go from this machine to another machine. So how do we do that? How do we have these internal to our network addresses? For instance, like if I'm talking wirelessly here, how does the wireless node know that I'm supposed to be sending packets upstream and that's supposed to be run to the internet versus something coming from there going down to here or to somebody else? What is that really done? So there's this protocol called ARP, or Address Resolution Protocol. At the link layer, and let me just show you this. The link layer, every single machine has a name. And the name is not an IP address. The name is actually something like, where's this? This. It's called the MAC address. So every single one of your computers and your phones and so forth, every single wireless card or Ethernet card that it has a unique identifier called the MAC address. And this is an example of a MAC address right here. It actually has a lot of information and it tells you what manufacturer it is and so forth. Let me guess who collects this information for us, yeah? Yeah, if you ever need to know where your MAC address is, call the NSA, right? It's a unique identifier for a computer. Also means that, for instance, software that wants to kind of know that you haven't pirated itself, it's going to look at things like a MAC address to kind of uniquely identify a computer, right? You can actually also fake these, which is a fun hobby. We can talk about that. Anyway, so that's how this link layer talks to each other. So this is down at kind of just above the layer where we're just sending bits of wire. This is how we figure out that there's some other node that's connected to the same router. And we're going to talk to that node. We're below the IP layer. So that's layer 2. So we use MAC addresses. We say like, hey, I know that you have this MAC address up there. I'm going to send this packet to you. Now, why was that decision made? It's because we somehow know that the node that we're talking to with that MAC address has also a specific IP address. Like in the example over here, this interface over here, whatever, has this level 2 MAC address over here, but also has this IP address over here. Did I lose you yet? Not yet. Good. Okay. This is kind of funny. So everything has two names. Every networking interface. So there needs to be something that translates between those names. Like, I need to know, I want to talk to this IP address here out in the world. And I want to know that I have this router. And my router is, suppose I look at this machine over here. What's my route here? My default router is this IP address over here. Somehow I need to know what MAC address to put down to get to this node. Otherwise, nothing happens. Right? So I need some translation between them. And that's what ARP gives you. So translation between the names at the layer 2 and layer 3, IP and MAC. So how would you design a protocol like this? In your beautiful utopian world. Yes, that's indeed exactly what they did. They created a protocol that works as follows. Hey, and look at the modern computers that they had when they decided this protocol, right? Like we were like really entering the 20th century here. Yeah, and those printers, like look at the printing. Even the 3D is on. So it would be like, hey, here's Jessica's computer. Jessica's probably really old by now. Jessica's like, hey, who has this IP address over here, 192.168.0.45? And it just shouts it out as a broadcast packet to all these different things over here. And then, yeah, what's going to happen? One of these devices is like, hey, it's me. Oh, it's me, and this is my MAC address over here. What could possibly go wrong with this?
Anyone can
Something
take
like
the
that means to you.
Exactly, right? Is there anybody here who has admin privileges? Yes. Great, okay. What? Like, you don't design protocols like this anymore. Anyway, so of course you can poison ARP. ARP poison works as follows. Hey, there's a packet here for 192.168.1.100, right? It's being sent here. Here's Alice over here. Router's like, I haven't seen this IP address before. I wonder what machine actually has it. So it asks everybody, hey guys, listen up. Who has the 192.168.1.100 packet, just like a packet waiting for them? And then one of them says like, hey, that's me. Alice over here. I don't know if she speaks like that. So here's my hardware address, he sends back. And the router now remembers, I'm like, oh cool, okay, next time I see a packet for that, I'm just going to remember that that was your MAC address, right? Not me. You can also use that here. What could possibly go wrong? Well, there's a cache that's operating here. It's so that you don't have to send this type of packet on every single request that comes into the network. You'll remember things for a little while. So guess what you could possibly do? You can send things up. Even if nobody requested it, you can just announce and be like, by the way, if packet arrives to 192.168.1.100, it's me. And everybody's going to be like, okay. And just like write it down to log and then like proceed with their lives, right? That's not easy, right? So, yeah, there's no authentication. It's a completely, fully trusting protocol. Everybody's friends and happy, right? So hackers, of course, exploit this to like snoop on the traffic, meaning that they sniff out packets to see what you're talking about and so forth. They just take a copy of all these packets and authentication information, can take over your sessions. They're going to pretend to be you. So if you're in a physical LAN, they'll be like, oh, I'm Catherine. I'm like, oh, I'm connecting to this weird site over here. Like, and then FTAs just go through the windows. That's why we have shields here. Or you can put a man in the middle where like, Catherine is talking to me and I'm talking to the internet and I'm getting a copy of all the juicy stuff she's saying. She thinks she's talking directly to the router, but she's actually talking to me. Let's think about that a little bit. So suppose you have a machine here, okay? And okay, we can configure IP forwarding to send packets to the people's LAN, blah, 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 blah. We're going to send to this switch here a fake ARP response. Because even if nobody requested, we're just going to say, hey, I am the router. Yeah, I've decided that right now I'm the router. Everybody, so if you want to send it to your default 192.168.1.1, that's me. It's my MAC address, right? You send that out and everybody's like, okay, great. now this victim over here, this poor person, is like, well, I want to send like this sensitive documents here to WikiLeaks or whatever it is they want to send. And like, you send it over here to the switch with the destination that you want to send it to. What was the MAC address for the router that you think you are, which is actually now sent to this person over here, this rogue Eve or whoever it is that is attacking the network right here. And now this person is like, oh, I got this packet over here. Okay, I can inspect it and shove it into my log of clandestine stuff. And then send it onwards here to the real router, to the internet. And packets come back, and then of course get routed to me because I'm the router. And then they get sent back here to Alice. And in fact here, this person never knows that they're not talking directly to whatever internet host, so they can authenticate and do things. NSA loves this. They've invested in massive infrastructure to be able to do that to anyone, anywhere. They actually have physical machines inside data centers in Italy and where not, where they can just like, oh, I want to take over that person. And now when they talk to the internet and they go to any website, they'll inject malware into that thing. Like, oh, you want to download Candy Crush. Here's Candy Crush with some extra candy, right? And like, yeah, you get it back and then take over your computer. That's what they do. That's why they're not really so concerned about encryption, because they don't have to break encryption. They just have to hack your computer where you have your key. That's how they operate, right? Anyway, we'll talk more about that. So man in the middle, this is a really fun attack. It's hard to detect. So whenever your SSL certificate or your SSH says, hey, somebody's doing something nasty, I don't recognize the certificate. What's happening? It means that you tried to have a secure connection to something on the internet, but really you're having a secure connection to this person over here, and they're then having a secure connection to the internet, and they're seeing all the unencrypted good stuff that you're doing, right? So like, oh, I'm going to connect them with Gmail. So, oh yeah, that's me, I'm Gmail right here. Here's my certificate. That means that this person here is now forwarding every single packet to the real Gmail, sending things back, and seeing all the intermediate information. Yeah. There are built-in tools in the Linux for doing this, by the way, just to kind of show you how easy it is. Okay, so TCP. This is what is contained in a TCP packet. So we have like an IP header right here, and the IP header has the source and the destination that I told you about, as well as a few other things like time to live, which we were exploring before to figure out how far we're going in the internet, the length of the packet, type of service, version, this is version 4 until hell freezes over when we start using IP version 6. The header checks on itself just to kind of make sure that we're not garbling everything in this packet, and some other goody stuff here. And in the TCP itself, it has some additional information, which are the ports. You guys remember ports, right? So port 80, what's port 80? HTTP. So if you have a web server, let me show you something. Let me just open up a browser here. I'm going to talk to google.com. I can say HTTP protocol and then just do www.google.com. I can do exactly the same thing and specify the port. I'm going to connect to port 80. And it just works, right? It's because by default, if I'm making a TCP connection for web-based stuff, the default port for that is 80. For SSH, default port is 22. And so on and so forth. There's like huge number of these ports that it's good to know. It's here in ETC services. These are all the ports you have to remember for the exam. Too bad it's closed book. No, I'm not that evil. Just, but I thought about it. Fun stuff here is SMTP. This is how you have your mail stuff. Time servers on port 37. Whois is on 43. So all sorts of good stuff. Fun. Anyway, so that's actually contained in the TCP header itself. What was the source port? What was the destination port? Then there's two things called sequence numbers, acknowledgement numbers. What are these? These are ways in which you can say, this packet was number 7, 8, 9 in this session. Very cool. Now, the acknowledgement is like, by the way, as I'm sending this packet, the last one I received from you was this one in your sequence. I acknowledge this part of your sequence. Just so the other party can be like, oh great, you've seen that many packets? That's awesome. Then I can finally get rid of them so I don't have to keep them around for retransmission later. Right? Whole bunch of little flags here. Urgent, acknowledging, sin, act, anyone? Push, Okay? This is things about, I want to establish a connection. In which case you say syn, I want to synthesize a connection. And then the other person is going to respond, oh, acknowledged. Yeah, I acknowledge your thing that you're trying to start a second. Actually, they start with they respond with a synac, taking two things together. Be like, I would also like to start a session with you. Let's be friends. And then you keep doing your stuff. And then finally, when you're tired of this person, you're like, yeah, I just want to end this thing here. It's not you, it's me. Or whatever it is that you want to say to the other endpoint here, right? And then, of course, all the data is, there's actually some other stuff in the header, and then there's the data that follows. All right, so let's look at the TCP handshake in more detail. When I want to start a new connection, for instance with Google, right here, here's what happens. I, as a client, I send out like, hey, yo, can I connect to you, please? And I send my syn back, like I say that it's a synthesis of new connection, and I put in some sequence number. Usually it should be something like 1, like it's the first packet of my sequence. The response is going to be like, hey, cool, yeah, I like that. Yeah, we should have coffee sometime, or like right now, in fact. And they send out their own sequence number, it's usually something like 1, right? And I acknowledge that you've sent out packet number 1, so you can discard that from your inventory, and then, oh, cool, hey, let's party. So it's like, synac, right? Isn't this how most of your, hello, what's up, right? Isn't this how conversations kind of go? Okay, this is the most sterile way of having conversations, but it's how computers do it. Okay, so, about these sequence numbers. Suppose they just start with 1. That actually means that Derek over here can create a connection on behalf of someone else, because there's nothing that limits you from putting in any source IP, any destination IP, in any packet that you please. Who's going to stop you? Right? You just injected a packet into the internet and it just like goes routed to where it needed to. The only thing that is missing is that if you wanted to see the response to your packet, it's going to get routed to the other person you're attacking. So that's not very useful. So you can kind of have blinded injection into TCP. Now, to prevent that, people decided that, like, well, maybe it's not a good idea to just start all the sequences at 1 because it's so predictable. Or if there's an existing connection going back and forth, I can be like, oh yeah, okay, we're just ha 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 ha, and then like somebody injects a packet and be like, I hate you, and like it becomes a part of the conversation. You can do that because you can predict the sequences. So, effort was made to try to make the sequences not predictable by having a random sequence number to start and a random acknowledgement number, which means that Derek, when he's trying to attack our connection, he has to guess exactly the right sequence number. It's just a 32-bit integer, which has how many possibilities? What's his ballpark? Meant a lot.
A billion?
At least a billion?
4 billion.
Yes, 4 billion, yes. So you have to have 4 billion packets before you would succeed, which is a lot, right? As you just would say. So it's actually really hard for you to inject packets into TCP for this reason. UDP, haha, no problem, right? There's no connection. So, if I wanted to check whether or not a port is open, so suppose I'm in this nefarious hacker, say Derek, and I want to just check to see if there's a port open somewhere. I want to see if this server that I'm trying to attack here is a web server loaded, or IRC server, or something obscure like that. I could just connect with it and say like, hey, I want to connect to your port 667, which is the IRC port. And the other's going to respond with, yeah, that's cool, let's have a connection. In which case you just acknowledge it. Or you can send a send and you get back an RSD being like, that port is closed, dude. Or you might even not get a response, in which case you just deny access. Now, let's think about how you would, how you could do something slightly different to figure out whether or not ports are open. One thing you do is just to say like, hey, we should hang out sometime. Oh, I'd love that. And then you just like walk away. Right? In which case you don't send an acknowledgement. You just know that the port is open. Right? You've not finished your handshake, so you don't establish a connection. It's one way to check whether the port's open. It's kind of rude, but this is about it. We'll see some more elaborate techniques. Let me first talk about a little bit about TCP spoofing. So, as I said, we can forge packets to come from wherever. To do so, we'd have to guess the sequence number, and so we don't see the responses normally because we're spoofing it from somebody that we're attacking. And so, what what NSA has been able to do is to do the same exact thing, except they see so much of the intermediate routers on the internet that they can figure out what the responses are. So they can inject packets into connections as well. And GCHQ, Great and some others have amazing ability to do this thing. Right now, this is actually in fairly good hands right now, this spoofing business of sending packets from anywhere, because backbones and part of the internet, they have protections that say like, hey, cool, a packet just arrived into my network, but it didn't come from the right place where it's supposed to go, and it's not going to the right place where it's supposed to go. I'm just going to filter that out, because that can't be good. There's a lot of filtering that happens like that in ingress and egress that make sure that some of these packets get filtered out. But I would say there's about 20% chance that people can inject things into your packets, whoever can do that. Okay. You guys remember this episode with, what was it, last week, when DYN was taken down, didn't the DNS server? Yes, where half of you guys probably suffered from this, like, Facebook stuff or something like that, no? So here's one way in which you could do that type of a flood that was done. You could have a SYN flood. So suppose you had to send a packet here from a client and server that says, hey, I'd like to connect to your port 80. I'm a web client. And the server responds back, oh, that's awesome. Yeah, it was totally hang up. Right? In which case you're supposed to respond to that. Right? But if you don't respond to that, this server here still is waiting for, like, still has an open invitation, has a chair waiting lonely for you to kind of come back. And eventually, after some time, it'll time out and be like, just didn't show up. Right? Suppose you're really evil. You do this serially. You're like, hey, we should hang up, hey, we should hang on. Like, you just keep sending this request. And the server's like, yeah, cool, okay, okay, oh. And then gradually just kind of choke up and get overwhelmed with requests because you need to keep state for every single connection attempt. That's an example of a flood. It's called the SYN flood. This was a huge dilemma on the internet for a long time. If you sent all the SYN requests from anyone, you would overwhelm, you would have to take over all the memory that was allocated to TCP requests in the kernel, and server was like, yeah, I'm kind of overbooked. I'm seeing a lot of other people, right? And so you wouldn't accept new connections to your web server. So Google would be like, yeah, we're kind of down right now. It's not cool. We actually have everything we need to be able to overcome this type of flow. So everybody's like, oh, this is the end of the internet. Let's find something else to do. Until this little weird guy, DJ Bernstein, came up with something called SYN cookies. DJ Bernstein is a professor, I think, at UC Chicago or something like that. He's the kind of like this kind of quirky crypto guy, extremely smart. He's the kind of guy like, so he was working in crypto, and the U.S. government was saying like, hey, you can't export that to other possible enemy countries because this is munitions. These are arms, right? Yeah, according to our I don't know, constitution or whatever they were quoting. Yeah, you totally can't do that. So he's like, oh yeah. So he sued the U.S. government and won. So it's just like, yeah, it doesn't go down without a fight, right? Spent several years just like, oh yeah, I'm gonna get that fixed. This is why we can now work on cryptographic algorithms and export them to whatever, because it's an expression of speech. Gotta love it. Anyway, so he came up with this idea. He's done a lot of cool stuff. He was like, well, actually, why do we need to keep any state here at the server? Suppose somebody connects to us. Do we really need to reserve like a table, like a chair at the table, right? What about we just, instead of sending like these random sequences back, we actually encode some information in the response that would tell us that when we get that acknowledgement later, we can reconstruct everything that we knew right here. Right? That's exactly what it does. So effectively, you just go here and be like, oh yeah, oh that's awesome. Okay, yeah, we should totally hang out. Like here's my acknowledgement number, and it's my serial number, or like whatever it is that it's the number of the chair that you're going to get like when you get here. And then you just forget about this person. And if you get an acknowledgement, they bring back this kind of note. I'm like, oh right, yes, I must have sent this. I don't remember it. I was so wasted. So you come in here and you're just like, okay, yeah, this looks like my handwriting. Fine, okay, you have this seat over here. Okay? Really cool idea. It's done by taking the timestamp of when things happen with something you don't have to worry about, with the hash of the IPs and the ports. So the only way somebody could have actually cryptographically done this, like so it's cryptographic hash, the only way somebody could have reconstructed that number was to be this server and have the information that's on the server. So you can recover what's called a cookie. It's a really cool idea. Anyway, so everything. Let's do a TCP scan here. Okay? So hackers, they want to know what ports are open, because each of these ports could be running vulnerable services that may be vulnerable to some buffer overflows or something like that. Right? That's what hackers tend to do. You try to pivot it to new machines, right? So this is your reconnaissance. You're trying to see like, hey, there's a server here inside this network that I'm hacking right here. In the Pentagon, there's like a server over here, and I might be able to get access to some more information. Let's see what it's running. So we can send packets and be like, hey, is port 80 open? We talked about this just earlier, right? So instead of sending like full port open, port close, you can do something a little bit stealthier than that, because that's pretty noisy. Somebody who's a network administrator is like looking at the network traffic and sees like, hey, it's port 80 open, 81, 82, 83. They see like this one node that's like going really, really social. Let's raise some alarms, let's say. So you want to be a little bit more stealthy than that. Walking into who's open, right? How do you do that? So, here are some ideas. You can set different flags. For instance, of all these things here, like we've been using SYN and SYNAC and stuff, but what if you just like do what's called the Christmas scan? You just light up all the different flags and be like, yeah, let's send that over. It's a packet that nobody's supposed to be able to receive because it makes no sense. And the response that you get back from it is like, either like, or it's like, yeah, well, this port is closed, and I don't know what you're doing. Okay? In which case, you've gotten information from when the port was open. You sent this kind of really goofy, it reminds me of with this weird package. It's my brother-in-law. He's like, hey, I found this great way of like the computer science. I found this great way to like go through a crowd. It's like a lot of people. Like, oh yeah, no, I can. You just do like this. And then people just let you through. It was just like, have you thought about the implications of it? And then he had, and he was like, oh, yeah. So that's kind of Christmas scan. You sent this really weird packet, and like, yeah, it's either not received or like, you know, just go away. Right? Null scan. You said no flags. You're just like, and either it's going to be like, I don't know what response, or we're close to right here. Yeah, find something else to do. Back scan. You said like, hey, welcome. Yeah, we should hang out. Or like, I appreciate you inviting me to hang out. It's your first thing that you say to the person. In which case, you're also going to get like, hey, okay, if the port is open, you're going to reset. Like, this is the wrong part of the protocol. You're not following the protocol. You didn't send us in, right? So you get this weird kind of responses back. And these things don't show up in logs as much. Window scan. Send like, hey, I'm willing to talk to you, and like, we should talk together and exchange messages of 0 at the time. Which doesn't make any sense to anyone. In which case you also get like, hey, you get a 0 window if it's closed in some operating systems. So, okay, all of that is kind of old stuff. Here's something really cool. Suppose you want to do a really, really stealth scan. It's called the idle scan. I want to know whether or not this target machine here is a particular port open. Okay? But I'm not even going to touch it directly. What I'm going to do is I'm first going to send out a packet here to some machine, some victim machine of mine. This is my machine that I hacked somewhere in, I don't know, some other continent, right? I went in there and I sent the SYN packet and I got back a SYNAC. And I actually get, as a part of that, some extra information about so-called IP ID, which is kind of the serial number of the packet that this node received. Now I'm going to spoof a packet coming from the blamed machine, saying like, hey, is port, let's say port 3, is it open? Machine here receives that packet, thinking it comes from the blended machine, and responds to the blended machine. In other words, like, yeah, cool, we should hang out. And this machine is going to be like, what do you mean, hang out? I didn't send anything like that. It's going to send a reset. Right? Or it's not going to send a packet at all, in which case, no hard feelings. Right? And then later, you send another packet to the blade machine and you ask, like, hey, we should hang out, and you get acknowledgement with the IP ID, which is either going to be 1 greater than you sent last time, or 2 greater. If it's 2 greater, it means that there was a response sent back here going, who are you? Yes.
So the reset is the blame machine
Yeah, so the IP address is on this machine, it has a counter of like how many packets it sent, and it sends it with every packet for whatever reason. When it receives a packet here that makes no sense according to the protocols, like I'm getting a SYN ACK, but I never sent the SYN response. I don't want to talk to you. Who are you? Go away. And you send back into like reset your connection, something wrong is going on. So this is going to try to, this in fact determines the connection that we started here at port 3. But because this was sent here, next time we talk to the blend machine, the IP ID, this global counter how many packets it sent, would then be 2 higher, one for this packet that is sent to us, and then 1 for the packet sent to the target machine, or just 1 higher, in which case there must not have been any exchange between the target and the blend machine. Make sense? We differentiate that. Cool, huh? Yes, okay. Fingerprinting. The operating system is actually implementing different variants of TCP/IP. TCP/IP is an enormous protocol. Windows 95, 98, they tried for a very long time to have their own implementation of TCP/IP, which was so horrendous that in Windows 2000, when people tried to use fingerprinting, they're like, huh, it's Linux. Actually, it's previously. They're like, why is Windows Linux? And then Microsoft was like, we borrowed some code. So they just took the code from like previous the implementation of TCP/IP because their own was pretty broken. Now they have their own as part of NT and so on, things like that. But because there are different underspecified things in the standard about how you do things, different operating systems react differently to different circumstances. So for instance, Linux by itself differs from BSD, which is what's used in your OS X and some of your Macs. It differs from how Windows was implemented. So you can actually send packets, you get information about what's actually running on that remote site. So you can like poke machines and figure out even more intricate details, like what kernel are you running? What other software might you be running? Right? You can get all sorts of fun information about the other ones. And you can even just observe traffic and learn something about what's happening on the machine. Right? You can see, is it using syntropy? What are the time to live values? Is it according to the algorithm used in Windows or in BSD? What are the Windows access by default? So, right? So this is all part of reconnaissance that's happening inside an organization. Okay. We have 6 minutes for DNS. Should we just go ahead and do it? Plow through? Or any questions so far? All of this makes perfect, lucid sense to everyone? Not a leading question. How many people have followed what I've said so far? Okay. That's most times. Good, okay. So, well, they've been recording. Yay! Okay. DNS parameters. So let's do DNS here really quickly, since that's all of that. So most people can't remember simple things like these numbers, right? I mean, you're on the radio and like, call now, 57 pi, and you're like, well, I don't remember any of these digits that you're telling me. Why is it pi? I don't have a pi on my, what was this? So you don't really have good luck with having people remember things like an IP address, right? Like, oh, search the internet now. Just go to Google at 213.167.142.130. That's 213.16. That would never work, right? And they realized that pretty early on the internet that like this is a doom thing. So in 1984, they invented something called DNS, the domain name service, so that people can say something that's a little bit more human, like a name of a place, and get the IP address back. So this giant kind of directory of this. And when they decided that this directory should not be just like one big central yellow pages thing that's like, hey, here's everything, but distributed somehow. This is, of course, a design that Google didn't take to heart to feel like we will be the yellow pages of everything. Right? So DNS has this kind of nice distributed aspect here. So this is hierarchy, where you read the domain addresses from right to left, and you see that there's this big domain called .com. And somebody's responsible for the whole tree that starts with .com. And under that, you could have something like foobar.com, right? And that's somebody, that's like a subtree over here. And then somebody has www.foobar.com. That's a particular machine. Or somebody owns candy.foobar.com, in which case you could have peanuts.candy.foobar.com, or whatever it is. What's nice about it is that you can now fragment this hierarchy down into different authorities. You can say, hey, there's this giant root server here that owns .com, and then there's a server here that's responsible for foobar, so I'll ask soap.foobar.com. And then there's different servers with different organizations that owns all the candy stuff. So candy.foobar.com is delegated to someone else. Or you could change it all around and have a different thing that's like, these things inside the entity are under the auspices of foodbar.com, except for walnut candy, which is somehow very different, and it's handled by different servers, right? You can make any changes to this tree as you like. What this means is that there's this kind of authority that's like gradually delegated down this tree, and you're responsible for everything that's kind of below you, right? Make sense? That's what DNS is trying to do. Of course, if you're a hacker, where would you try to go? Yes, you try to go for like the very big root servers, right? If you can hack those, you can just take over the internet. Okay. That's what. Of course, these things are then monitored 24/7 by offensive staff and so forth. Now, in order to figure something out, suppose we're trying to figure out, we're trying to resolve some DNS request. Suppose I want to go to Syndis.is, my company. What we'll do is that the program is going to call a library called getHostByName. So it's like, hey, who is this Syndis.is? Something happens when you type ping Syndis.is or you type it into a browser. There's going to be a request now sent to some server to figure it out. The way it's done is that this library chain opens up a file called etcresolve.conf, which is this kind of block of thing that says, like, if you want to find names, you have to contact this IP address, or if that doesn't work, try that IP address. So this one here is a local DNS server. This one here is the Google DNS server, right? Okay, so you now send an actual packet to 130.235.50, which is your local DNS resolver, and ask about, hey, who's this in this thing? The way it works here is like some client over here, who is, I think, mysteriously absent today. And she's sending a packet from her IP address over here to the local DNS server, okay? So she sends it over, and what happens is that there's this kind of a transaction that's going on here, this transaction 6564, something like that. So a UDP packet is created that says, hey, yo, what's in this.is? Put the source and destination correctly, and the local DNS server may already know the answer. It just sends it back and goes, yeah, I know what it is. It's 4021. Okay, so it's a UDP packet sent back. Now remember, UDP is the unsafe version of internet communication, right? You send packets, they're not encrypted, there's no session, anybody can spoof them, right? So sometimes you don't know the answer. Like Reza might be asking the same question to the local DNS at different times, and say, hey, what's in this.is? And this local DNS has no idea. So the local DNS is now geared to talk to its upstream server and be like, okay, I know I have authority over this part of the internet, but now I need to talk to somebody superior to me. And eventually, you gradually can reach up to the root server, who should at least be able to help you on your request. In which case, you talk to the upstream DNS and the upstream DNS, and then maybe have a response and say, hey, yeah, it's 4321, and that goes back to Reza, and now this local DNS server has a copy of Syndis.is and knows it, and from here on, it's going to cache. Makes sense, right? Okay? So, of course, we can go further. Now, suppose we do something evil here. If we just look at the packets, what we'll notice is that when we trace the packets here, we'll see that there are these packets going back and forth here, and they're always being sent here from the same port on the DNS server. Why is this interesting? It'll unfold. And they're being sent to all these different, so 53 is the DNS port, being sent to all these different places at different ports. Okay, that's very interesting. So 9 guard, all this different requests. What's wrong with this picture? Well, let's figure out what's wrong with the fact that this DNS service was sending from the same source port. So, enter a hacker. Aaron comes along, okay? So Aaron says to be mount an attack against DNS here. So what's happening is that he's going to send a packet here to local DNS server saying like, hey, what's in this.is? And it's actually not going to send just one packet. It's going to send a whole bunch of packets saying, hey, what's in this.is? Okay? So far so good. And this DNS server is going to get every single one of them and then send onward, and here are the packets, hey, what's in this.is? Right? Always from the same source port. The only thing that's different between them is that there's some random transaction ID attached to each packet. Everything else is identical between every single packet over there. Why is that important? Why is that important? Well, because what we're going to do next is we're going to say, we're going to have Aaron over here spoof responses as if they came from this server that this DNS server is talking to, and say like, actually the answer is 6666666. It's just going to send a whole bunch of packets with random IDs over here, just as if they were responses from the upstream DNS server. So wait, what's happening? We're sending requests to this DNS. They're opening up, say, some K number of of requests for synthesis, and then we're spoofing another K responses. What's the chance that any one of these IDs here will match any one of these IDs over here? Likely, unlikely? It's the 16 bits. What's that?
Pretty poor.
Pretty poor, right? Yeah. I'm not gonna tell you the answer. I'm gonna leave it at that. We'll come back to it on Monday. And I'm gonna tell you that the answer is amazingly high.